That's Julien.
Okay, bonjour, hello everybody. It's my pleasure to introduce Deng from Université de Lorraine and CNRS. As written on his slides, he will talk today about big Picard theorem for varieties admitting nilpotent harmonic bundles.
Okay, so thank you very much for the invitation. Thank you, Steven Wu and Julien. So it's my great pleasure to present my recent work in Montreal seminars. Actually, so this is my first time to give my talk in Canada. So good memory for me. Okay,
we have to invite you over.
Okay, thank you. So yeah, so for me, I want to say present my recent work on big Picard theorems, but for some varieties which admit in nilpotent harmonic bundles. So actually, this is a joint work with Benoit Cadorel, who was a Met conférence aussi announced. It's my colleague. Okay, so let me start. So first, I will we start with some introduction. So let's recall the Picard theorem. So actually, the Picard theorem consists of two parts. So the first part, which is called a small Picard, little Picard theorem. So I think it's over 100 years ago. So it's a very old theorem. It says that for any there exists no holomorphic map from the complex plan C to P1 minus 3 points. Okay, so this is the little Picard theorem. And there's also a stronger theorem, which is called the big Picard theorem. So also proven by him, and say that so any holomorphic map from the punctured disk, so I denote to be a delta star, which is just which is a punctured disk. So Z here is just a norm greater than 0, less than 1. From the punctured disk to also P1 minus 3 points is distinct 3 points. Then extends to a holomorphic map from the unit disk. So just I do know to be delta in this lecture. To P1. So this is the so-called great Picard theorem, or big Picard theorem. So from the name, we know that it should be stronger than this little one, but actually the proof is very easy. So, so to show the big Picard theorem, so it will imply the little one. So you just argue by contradiction. So you say that, okay, assuming there exists a holomorphic map from C to P1 minus 3 points. So I write simply, it's just a 0, 1, infinity. But then you compose it with the exponential map. You compose F with the exponential map. So it's still the C to this one. Okay, but then, so we look at P1 as a compactification of C. We look at P1 as the union of C with a point at infinity. Then by the big Picard theorem, so we apply the big Picard theorem, we know that this holomorphic map will extend across the point at infinity. So in other words, so there exists G, which from the P1, just the extension of F composed with exponential map to P1. So which extends this map, but from this one we know that for instance, so G inverse, so the inverse image of G, for instance F, so F1 here, so it's an infinite set. So it's not a finite set. So it consists of 2 pi I times m here, where m is the integer. Okay. So therefore, but it's a holomorphic map between between P1 to P1 compact Riemann surface. The map has finite fibers. So therefore, a contradiction obtained. And we show that how to use a big Picard theorem to prove the little one. So these theorems, so actually, so they are very deep result at that time, but they are also modern some starting point of the modern hypothesis. So let me now move to the more recent things. Okay, so for the generalization of little Picard theorem to high dimensional. So this is a definition of people which is called a Brody hyperbolicity. I mean, a complex manifold, the definition is easy. So a complex manifold, so X, so it's called a Brody hyperbolicity. Bolic. So if there exists no non-constant holomorphic map from F to X, just like the little Picard theorem. So you P1 minus 3 points, it has no such a holomorphic map. Then it will be called a Brody hyperbolic. So, and then, so this is the generalization of the little Picard theorem to an arbitrary complex manifold. And actually, so this is very important because the modern hyperbolicity just using this notion to study the varieties. We wanted to see ways of varieties admitting those holomorphic maps from C to him. So it's a very interesting subject. So because there's a conjecture by Green, Griffiths, Long, who say that a variety, if it's of general type, then it should be a pseudo Brody hyperbolic. Namely, so there exists a proper subvariety so that all the entire curves lie in. But now I want to say something more general. So because as I say, so this is a generalization of the little Picard theorem. I want to introduce a notion which is stronger, so that as a generalization of the big Picard theorem. So let me give the definition. So it's slightly complicated because as we see, so P1 minus 3 points has some compactification of a complex manifold. So therefore, in order to formulate this generalization of big Picard theorem, we have to do something a bit more. So let me give the following definition, which I call a Picard hyperbolicity, which is seen as a generalization of big Picard theorem. So now let X be a compact Kähler manifold. Compact Kähler manifold. And let U be a Taritsky open set. So namely, so its complement is just a proper subvariety, closed analytic subvariety of dimension less than X. So then we say, so U, just this U is a pseudo, because sometimes we are interested in slightly weaker but more interesting things, pseudo Picard hyperbolic. So if there exists an analytic subvariety of X such that for any holomorphic map from the punctured disk to U, now it's on U, with such that any holomorphic map from the punctured disk to U with its image not completely contained in this subvariety will extend the cross origin to a holomorphic map. I mean, I made it FE bar from the unit disk to X here. So same say that, okay, so if there exists some proper subvariety of X, so that any holomorphism from the punctured disk to U, which does not lie completely on this proper subvariety, then it will extend to a holomorphic map from delta to X. So if you have such a property, it will be called a pseudo Picard hyperbolic.
Sorry, I have a question, if I may.
Yeah.
Why do you need the Kähler assumption for this definition to hold?
Yeah, in general, you don't need this one, but actually, we want to say, so I will say this later, because we want to say this this does not depend on the compactification. You see, this definition is only for U. Actually, we want it does not relate on its compactification. So if we lose this Kähler assumption, I don't know how to prove that this property does not own its compactification. So for instance, so if this holds for U, for some X which contain U as a theoretical open set, I don't know for any other Y which contains U. So we still have this property. This is a big problem for me. So therefore, the Kähler assumption was used for this property.
Okay, thank you.
Okay, but I will explain very soon why I need this assumption. Okay, so moreover, so this is pseudo, but if moreover, so if such a Z is an empty set, then we just reduce to the usual thing. If Z is empty, then we say just U is Picard hyperbolic. You just remove the pseudo Picard hyperbolic. Okay, so this is the definition of Picard hyperbolicity, and of course, from this very definition, we know that P1 minus 3 points is Picard hyperbolic. Okay, but I just come to the questions proposed. So why I need this Kähler assumption? Because as a consequence, I mean, not a simple result, but by a deep theorem of Hsu, of Yang Hong Hsu, I think in 1975, so long time ago. So if we if U is pseudo hyperbolic, then any other any other compactification of U. Maybe I did not do Y to be U. Namely, Y is another complex Kähler manifold, which contains U as a theoretical open set. It must be bimeromorphic to. So bimeromorphic to X here. So that's why that then implies that so this definition does not depend on the compactification, because if it holds for any F for X, then any holomorphic map from the puncturing disk to U extends to X, then you can pull back it to via this bimeromorphic map. It will also extend to Y here. Okay. So this is why I needed this assumption. But the proof is not hard, but we have to use a very deeper theorem by Hsu, some criterion to say when if we have an extension of one disk, then there's some similar result for extension from the polydisks. So, but this is something which not so read. I will not reprove the things here, just as a remark. Okay. So this is the definition of this one. But now the goal of the lecture was to see, okay, we want to, since we have the P1 minus 3 points is Picard hyperbolic, we want to find more example, so more generalizations why this should be true. You want to see a more general phenomena. So this thing is true. So for those two ways to look at the P1 minus 3 points. Okay, so P1 minus 3 points. So one way is from the symmetric space. So actually, so this is the up half plane. So you can think of so actually the P1 minus 3 points. So it's a quotient of the up half plane. by group gamma, where gamma is a second concurrent subgroup of the automorphism of group of H. So actually gamma is what? So actually it consists of the elements in SL2Z. So with modulo 2 here. So this subgroup, so actually is the up half plane. We know that this subgroup, the X is a subgroup, is a lattice of the automorphism of H. So and therefore, so the quotient exists so as a Riemann surface, and actually, so it's just isomorphic to this one. So then, by this factor, we want to see something more. So, okay, so this is just a Hermitian, the quotient of a Hermitian symmetric space by a lattice. We want to see whether this is generalization. This result holds true for any quotient of Hermitian symmetric spaces by some lattice. So this is one direction to see some generalization of the Picard theorem. And another point of view of this, so it's a base of the Legendre family of elliptic curves. So for the Legendre family, so it's just a family of elliptic curves to this. And actually, so the fibers defined, I mean, for any lambda here, so the fibers in an elliptic curve, so I mean, xt is a fiber here is actually defined by the following equations. -1. Okay, so P1 minus 3 points actually is the base of the smooth family of elliptic curves. And therefore, another generalization of this we want to see whether it's true for another generalization is whether for some geometric smooth families the basis should enjoy some hyperbolicity property. Okay, and actually for the second question, so it has been solved by in a joint work with Stephen Lu, Sun, and Zuo. So let me record it. So but it's really how to say, it's spend a lot of time to do that. So joined with Stephen Lu and Sun. I don't know whether Sun was in Montreal for the postdoc now, and Zuo. So I think 2019. So we proved that the stimuli is a bit complicated. So it's corresponding to the hyperbolicity of modular spaces. So assuming okay, let so X to Y be a smooth projective family. Of polarized manifolds with semi-ample canonic boundary. A polarized manifold will fix some ample polarization. So then, I mean, by the work of Fiedeg, we know that there is a modular spaces corresponding to these polarized manifolds with some fixing here polynomial. And therefore, assuming, so since there are the modular spaces, assume that the modular map, or just the classifying map, I did mu to the modular spaces of those polarized manifolds with Hilbert polynomial is quasi-finite. So namely, have finite fibers. So Y is a smooth quasi-projective variety. Okay. Then we prove that Y is pseudo. Sorry, is just a Picard hyperbolic. So this is a vast generalization of the second point of view, because the P1 minus 3 point is just the base point of the Legendre family. So, but here it's any polarized manifold with semi-ample canonic boundary. We can prove this result. Okay, so but today I will not talk on these generalizations. I will talk on another generalization in this direction. As I say, so in this direction, so you want to see is this result holds for any quotient of Hermitian symmetric space by arithmetic lattice? Okay, so actually the answer is true. So in this direction, it has already been solved actually. So this is a theorem by which is Kobayashi and Ochihai and Borel also. I think in 78, something like that. So X is a quotient of the bounded symmetric domains. I denote to be D. So where D is a bounded symmetric domain. Symmetric domain. And gamma is the lattice of the automorphism group of D, which I mean lattice acting on D. So then acting freely, so therefore it's a smooth complex manifold. But actually, so Borel has proved that, so we know that by the theorem of Bailey-Borel, we know that X is quasi-projective manifold. So therefore, when it's quasi-projective, then it's also an open set of projective manifold. We can say whether it's Picard hyperbolic or not. And actually, so they prove that. So they prove that X is Picard hyperbolic. So it's at that time, so it used very difficult result because they have to use in the compactification, which is the so-called Bailey-Borel compactification of this quotient of bounded symmetric domains to get their hyperbolicity. But as we will see later, so I in this talk we'll find that okay, I can give a simpler proof without you knowing anything on its compactification. So this is the generalization of the P1 of the Picard theorem in the first direction. Okay, but you will say, okay, then the story ends. So can we say more on this? But actually, that does not end. So this is not the final form because bounded symmetric domains are something there's some even more general objects on that. So which is called the variation of Higgs structure, the period domains. So I will not talk too much on this the variation of Higgs structures or period domains because it's not so related to this talk. I will speak even more general. So the period domains are just modular spaces or just classifying spaces of polarized Higgs structures. So actually, in general they are not algebraic. So since they are not symmetric, so they are not just not algebraic, not a quasi-finite or something like that, or not algebraic, and they are only homogeneous. But we can say something on it. So I mean. So I can prove that, but they are really a generalization of, but they are generalization of bounded quotients or bounded symmetric domains. Because quotient of bounded symmetric domains can also be realized as the modular space of some polarized Higgs structures. Okay, then you won't see what's the formulation of the in this direction for Picard hypothesis or Picard theorem. But then since it's not algebraic, we have something to do. So this is some theorem which I proved maybe 2 years ago, 1 year ago. So the statement is the following. So let X be a quasi-compact Kähler manifold. Compact Kähler manifold. By quasi-compact Kähler, I mean it's a theoretical open set of a compact Kähler manifold. So therefore, it fits very well in our setting. So assume that there is a variation of Higgs structures, a complex variation of Higgs structures. I first write a complete word. Complex variation of Hodge structures on X. So since the family, this means that there's a family of Hodge structures parameterized by X, and it parameterized in some special way. So this is called a complex variation of Hodge structures, but such that, so we want it to be parameterized in a maximal way. So namely, we don't want Zx is just a trivial thing. So no changes of the variation of Hodge structures such that. So since it parameterized all the Hodge structures, so therefore there's a map from the from X to its modular space or classifying space of Hodge structures, which is I call a modular map or classifying map. So the corresponding classifying map, I denote to be mu, still mu here to X to the, as D is a period domain. So I have to define this in this way. Here I cheated a bit since we have to consider the monodromy, but I can take a universal cover of X. So has finite fibers. So has discrete fibers. Then, so I prove that X is also Picard hyperbolic. Okay, so just one word. So actually, so this is a generalization of the theorem by Borel and Kobayashi or Chihai, since we know that for any so as I say, so for Hermitian symmetric spaces, quotient of bounded symmetric domains by some lattice, so they can always be realized as a modular spaces of variation of Hodge structures. So therefore, one can always construct a complex variation of Hodge structures over quotient of bounded symmetric domains by arithmetic lattice, such that the pure map satisfying such a property. So therefore, it will be give a new proof of the theorem by Kobayashi or Chihai. But today I want to talk something more, since actually, so the variation of Hodge structures is not even a more general statement. I think the more general statement is Higgs bundles, and I will talk on this. So now we will move to the main scenes today. So some technical things, and I will explain the main result I want to prove. So let me, so Higgs bundles, okay, or harmonic bundles. So actually, so the definition of Higgs bundle is very easy. So let X, so Higgs bundles. So let X be a complex manifold, just no summation and compactness or something, any complex manifold. So a Higgs bundle on X, so it consists of a pair. I mean, I did E and a theta such that where E, so where E is a holomorphic vector bundle. Vector bundle, and theta is on the morphism of B with value one forms with values in the morphism of B. It's OX morphism. Such that, so the theta with theta is 0, identical equal to 0. Yeah, so the definition is such a symbol. So you require just a vector bundle together with the morphism of E with values in one form, such that you have the following, which is called the integrability condition. But why Higgs bundles? I just want to say why this motivation actually. So from Simpson's point of view, so it comes for a complex variation of Hodge structures. You can always take in, because you have a Hodge filtration. Then when you take in the gradient of the Hodge filtration, the Gauss-Money, you restriction the Gauss-Money connection over this every gradient pieces of the Hodge filtration, you will get automatically a Higgs bundle. So by the work of Simpson, we know that. So therefore, so it's it can be seen as a generalization of variation Hodge structures. But so we know need some metrics. So now more generally, so more specifically, so let me call definition. So which is a harmonic bundle. So actually, so a harmonic bundle is a triple. So where E theta is a Higgs bundle, but you have a metric is a Higgs bundle. And H is a smooth Hermitian metric. For E, such that the connection defined by first the Chen connection. So this is a Chen connection. This is the 1-0 part of the Chen connection. So this d bar is the d bar of E. Okay, so I mean here it's a Chen connection, but it's not the end. So plus theta and plus theta bar H here. So theta bar H. So it's the adjoint of theta with respect to H, the smooth Hermitian metric. So such a connection, the Chen connection plus this self-adjoint operator is flat. So when such a theorem, when such a H exists, so it will be called a harmonic metric for the Higgs bundle E theta, and such a triple E theta H will be called a harmonic bundle. Okay, so so you want to see why we need such a very strange things, because when you decompose the variation of Hodge structure, actually when from the variation of Hodge structure nabla, you decompose it in several pieces. So according to its decomposition, so with the Hodge decomposition, so you will see that theta is just a correspondent to the Kähler-Spencer map, like so, and this joint is just its dual. So it will be you see the arise of very naturally it's a complex variation of Hodge structure. And from another point of view, so if you consider a representation of the a semi-symbol representation of the fundamental group of any compact Kähler manifold, so by the theorem recall it, you will automatically have such a call it and Sue Sampson, you have automatically have such a decomposition of the flat connection. Okay, and but I'm more interested in this following object, so which is called nilpotent harmonic bundle. So just as in the title you will see. So simply, so sorry for so many definitions, but I will soon use them. So definitions, so which is called nilpotent. So, harmonic bundle. I mean the definition is easy. So I mean, so a harmonic bundle E theta H is called nilpotent. So if the Higgs field, so theta, so if you look at this one, so is nilpotent for any Xi in Tx, because we recall that theta is a morphism of E to E over this one. So if you take an evaluation on any Xi in the tangent bundle, so then you get a morphism, anomorphism of E. Then you require that for any Xi in the tangent vector field, tangent bundle, then theta E as an anomorphism of E is always nilpotent. So this definition also generalized. So because the variation of Hodge structure is automatically nilpotent harmonic bundles. I just a remark. So this is a generalization. So a complex variation of Hodge structures, the category of complex variation of Hodge structures belongs the category of nilpotent harmonic bundles. Sometimes when we prove one theorem, we want to see, why it should happen. Is there some more general expectation of this theorem? So now I just want to present the main theorem as a generalization of my previous theorem. I say, okay, so for complex variation of Hodge structures, we have the theorem like Borel, Kobayashi, or Chihai, but then actually is this more general setting is also true. So this is the theorem which I want to talk today. So it's with Cadorel. So in 2021. So let X be still a quasi-compact Kähler. Kähler manifold. So assume that there exists a harmonic bundle, a nilpotent harmonic bundle. Harmonic is theta h over x such that, so we don't want this harmonic bundle to be something trivial. So therefore we require that theta is injective at one point, a general point. So here theta you can write, you put you can put this one, the form here, and you move this to here. Then it will be, you can also think of theta as a morphism from Tx to the anamorphism E, just as since I wrote there, is injective. Is injective at general point. At general point. I mean, namely, this is the morphism is injective outside outside a heuristic, outside analytic subvariety of X. Then the statement is that X is pseudo Picard hyperbolic. So here you cannot expect the Picard hyperbolic since you can always blow up any points. So that then this condition is always verified. But if you blow up any points, then you have P1, Pn, some exception divisors, then you have a lot of rational curves, but then it cannot be Picard hyperbolic since. So therefore, you have to make this pseudo Picard hyperbolicity here. Hyperbolic. Okay, but if you assume that theta is injective everywhere, then you can expect, then it's true. Then X is Picard hyperbolic. You can remove the pseudocity. Okay. Okay, so this is the theorem I want to talk today. Actually, so we can say more. So recall, I mean, there's another interesting theorem which but I think I have no time to give the proof. But I would just state it is the same thing as us. So actually, we can have more. So the same setting. The same setting as above. Then there exists maybe I did a mu, which is a finite unramified cover. Ramified cover from a quasi-compact, quasi-projective manifold x theta to x such that so any compactification, not only x theta is hyperbolic, but any compactification and x theta e bar of x theta, because it's quasi-projective, then we can say projective compactification is also pseudo Picard hyperbolic. You have to pass into the ramified cover, unramified cover. For instance, for P1 minus 3 points, so then its compactification is only P1, then it's not a hyperbolic. Okay, but if you pass into some adding some level structures, then I mean you can pass into some covers, then you can achieve this. There will be some higher genius. Its compactification will be higher genius curves. Then it's always a hyperbolic. So this is the theorem which is stronger actually. So it's not only pseudo Picard hyperbolic; it's of general type. So its compactification is also of general type. Why are you interested in such a theorem? Because I think so. NATO. So actually, so remark. So NATO, so in 1989, has proved a similar result, proved a weaker result for boundary symmetric domain for X is equal to any boundary symmetric domains by some, the quotient of boundary symmetric domains by some lattices. I mean, where these boundary symmetric domains. Okay, so therefore this is also generalization of the theorem by Nadel, but later Nadel's theorem was improved by Evan Husserl, but I don't have time to explain this. Okay, so now the rest of lecture, I have 15 minutes. I will just explain the idea of the proof. So now I will go to the proof. Actually, so the proof consists of two parts. I will mainly discuss on this one. So assume that X is quasi-compact Kähler manifold and there is a nilpotent harmonic bundle, such that the Higgs field is injective, theta is injective at general points. Then X is pseudo-Picard hyperbolic. Okay, so I will explain the proof. It consists of two steps. So first, we will construct a pseudo-Kähler metric, pseudo-Kähler form, or you want it, on X such that, so it's holomorphic, I denote omega here, but it's holomorphic sectional curvature. So you are less than some negative constant. So this is the first step. So by pseudo-Kähler form, I mean omega is semi-positive but strictly positive at some theoretical open set. So and also d omega is 0. So here maybe I write word. So this means that omega is semi-positive, closed, and also so strictly positive at some over some theoretical open set. We can still define the holomorphic sectional curvature. I mean, you just define it over the place where it's strictly positive. Then you say, okay, it's minus then this one. This is the first step. And the second step is just to prove criterion, some criterion for pseudo-Picard hyperbolicity. So actually, so this is something something close to what we have done with Stephen and Sun and Zuo. But actually, the proof is slightly different since before in our previous proof, we both using nonlinear methods, nonlinear theoretic methods. But at that point, so we're using some Finsler matrix, but the matrix has a very clear behavior near the boundary. But here we see the matrix are only defined on X. There's no information on its boundary. I mean, if you take X to be any compactification of X bar to be any compactification of X, we only know that on X there is a pseudo-Kähler form, but we have no information on what's its behavior on the boundary. Then we need to some work to do to overcome some problem that. So this criterion just is on this one. So let me write this criterion. Then I will show what the criterion is the following. So it's a theorem with still with Benoit and myself. I mean just the same thing. So let X be a quasi-compact Kähler manifold. So assume there exists a pseudo-Kähler form on X, I don't know, maybe omega, such that its holomorphic sectional curvature of it is less than 2 pi minus c. So I put 2 pi for some special reasons, for some constant. Then there are two consequences. So first, just this one is enough to show the pseudo-Picard hyperbolicity. And I will not write here. And if omega is a Kähler form rather than pseudo-Kähler form, then X will be Picard hyperbolic. So therefore, for this, it will, as I answered the first question, it will give a rather easy proof of the theorem by Borel, Kobayashi or Chihai. Since for bounding symmetric domain, the Bergman metric, we know that it always has a holomorphic sectional curvature negative. But therefore, applying this first criterion, we give a simpler proof of the theorem by Borel or Chihai. Okay, and moreover, so x e bar is a Kähler compactification of x, which is a Kähler compactifying x. Kähler compactifying x, and if so, I first write it, then I explain the notions here. C B. Then the compactification is also pseudo Picard hyperbolic. Let me explain the notion. So here, D is the boundary divisor of x bar minus x. So since we can always assume it's symbol normal crossing divisor. Since we can, if it's not a symbol normal crossing, we blow up, then we'll make it to be symbol normal crossing, the boundary divisor. And omega e bar, so is the positive closed one current on x e bar, which is the extension, which extends omega. I mean, there's many ways to do this such extension, but this is a trivial extension. I mean, you just take the because the coefficients, you just take the trivially to be zero over this this component. Then it's not smooth, it's just a current. But by the theorem of then we can prove that the point is that since the holomorphic sectional curvature is negative, we can prove that its volume is locally bounded with respect to any smooth metric on x e bar. And by the theorem of Skoda, so we know that such an extension is still a positive closed one current here. And the theorem says that, okay, so if for such a Skoda extension current, so it says cohomology class H11 class, and it minus C over D. So D is also a 1-1 class in x e bar. So if there are difference, C is just as a constant here of the holomorphic sectional curvature. So if the difference is big, then x e bar will have more, then not only x is pseudo Picard hyperbolic, it's any of its compact Kähler compactification is also pseudo Picard hyperbolic. So the second statement was used to prove this one, prove that we can find find unramified cover of x such that any compactification is pseudo Picard hyperbolic. But to find such a covering, we need some work to do how to find this one. So in the rest of talk, I will explain the main ideas of the first and the second proof. So 5 minutes. Okay, so let me explain the main ideas. So the fourth, so main ideas. So first, let me prove that x is x equipped with pseudo Kähler metric. So how to define this? So recall that theta is something on the endomorphism of E here. Okay, and for endomorphism of E, so recall that we have a nilpotent harmonic bundle here. Then for the endomorphism of E, so it also equipped with the harmonic metric. I mean, because any metric on E will induce the nature metric on endomorphism bundle. So therefore, you define a metric, I denote maybe Hx for this, and Hx is defined by, so I mean for every U and a V, which is of Tx. So you define a Hermitian metric to be defined in this way. So you use theta to map the U here, and you theta V, because theta U and theta V will be something on this endomorphism of E. I assume theta is injective, okay? Then there will be a section here. Then I'm using the harmonic metric to do the evaluation to define this one. So then one can prove that this is so this is just the Hermitian metric here. I mean the associated form 1-1 form is just omega will be minus I trace theta G bar, where theta. So here we record the theta H bar is the adjoint of this theta here. So one can show that the associated form is in this way. So to show it close, then we can see that, okay, you take the d omega, you have this one, and it's equal to trace. So it will be d is the chunk connection of this one, and plus I trace d theta. By the harmonic, by the property of the harmonic bundle, this and this will be both zero. So therefore we get the closeness of this one. And then with more work, so we can compute the holomorphic sectional curvature, but just by some calculation of the curvature. I mean, there's some small tricks to do this, but it's not so hard. So then we can show that the holomorphic, the bisectional curvature is always semi-negative, and the holomorphic sectional curvature is strictly negative. So this is something on the first part, on the constructing a metric here. I mean, this is for variation Hodge structures, we already know this, because for variation Hodge structures, by the work of Griffith-Schmidt, you can pull back the metrics on the period domains. Then their work showed that, okay, the pullback metric has always holomorphic sectional curvature negative. This was already known. So in our paper, so actually we do the computation for nilpotent harmonic bundle, and in some sense we can also give a simpler proof of the difficult result by Griffith-Schmidt. So this is the first part, and I just say a few words on the second part. So on the criterion, I mean, how to do the criterion. So it's actually nonlinear theoretic. So for the criterion. Okay, so actually, we will use such an extension. So one closed positive current, because actually omega is not defined over the whole X. Okay, and to show any holomorphic function f extends over the compact Kähler manifold extends. So there's a way in the nonlinear theory. So okay. So let's regard this. We take z to 1 over z for the punctured disk. Then by this transform, so it will be some z over c here. But actually, so z its norm will be greater than 1 after you transpose this one, and say f extends to delta star. Extend to the origin, then in this formulation of in this characterization of delta star, it will say, okay, f extends to infinity. Then a theorem in nonlinear theory, so say that you can define a characteristic function in this way. So then 2 minus t here. Okay, f star omega x bar. Here, omega x bar is a Kähler form on the compactification, smooth Kähler form on the compactification. And the nonlinear theory told us that, so if this has a growth of log r when r tends to infinity, then f will extend across the point at infinity. So it's already known. We already know this for projective manifold, but actually for Kähler manifold, it's not written in the literature. So we have using some Bishop theorem to show this, but it's not hard. And then now the problem is to reduce the question to proving this for the growth of this nonlinear characteristic function. Then you're using the things, because we already know that the holomorphic sectional curvature is negative. Then you evaluate this one, you will get something here, okay? But since f avoided the boundary point, so this also holds for the whole thing. Then you take this operator to both sides, okay? Then you are reduced to using some tricks in our linear theory. What you finally achieve that is you prove you get the following thing. We'll plus some O log r. There are some calculation we have to do. Here you will get something here, yeah, and some error terms. Here from the expression here, you will see that, okay, so So we can conclude that TF omega e bar R has low growth. I mean, by this expression. But the point is that omega so this is only a positive closed one-one current. It's not this Kähler form on the compactification. So this is only singular things. So it's not a smooth form. It's only a positive one-one current. So we have to compare this one with this one. And so need some work to do. So we can show that, okay, so when this has the low growth, then this has the low growth. So this really depends on the analysis of this omega e bar on the boundary. So near the boundary, this behavior is very mild, though we know that it has some singularities. But actually, the singularity is mild enough so that we can get a lot of information. So then we can prove the theorem. But this is some very rough ideas. So I have no time to explain. So okay, so I think my time has already gone. So okay, so I will stop here. Thank you.
Thank you very much. Thank you.